Types of bus arbitration. Daisy chain arbitration. Imagine a line of people waiting to use a single bathroom. Each person looks at the next one in line to see if the bathroom is free. In hardware, each device is connected in series. The request signal travels from one device to the next. The first device that sees a request and has the highest priority, usually the one closest to the controller, wins the bus. Simple, low cost, but the delay grows with the number of devices because the request must travel through every link. Parallel arbitration, like a group of friends all shouting at once to decide who gets the TV remote. All devices assert a request on separate lines at the same time. The arbiter compares the signals in parallel and selects the highest priority request instantly. This gives fast decision time constant 01, but needs many extra wires, one per device, increasing cost and pin count. Distributed arbitration, comparable to a round-table discussion where everyone talks and reaches consensus without a single boss. Each device contains a small piece of the arbitration logic. They exchange who has higher priority messages over the bus itself. The decision is reached after a few handshake cycles. It scales well to many devices and reduces wiring, but the protocol is more complex and latency is a few clock cycles. Arbitration protocols and timing. Binary priority encoded arbitration. Think of binary numbers as ID cards. Each device has a unique binary ID. During arbitration, devices broadcast their ID bits starting with the most significant bit, MSB. If a device sees a 0 on the bus while it wants to send a 1, it knows another device with higher priority is present and immediately drops out. The winning device's ID remains on the bus. This is how PCI and VME buses decide the master. Token passing, similar to a relay race baton. Only the device holding the token may drive the bus. After it finishes its transfer, it passes the token to the next device in a predefined order, often a ring. The token eliminates contention because only one holder exists at a time. Token ring networks and some USB implementations use this method. Central controller bus controller arbitration, like a traffic cop at an intersection. A dedicated controller, for example the memory controller in a system bus, receives request signals from all devices, decides which request wins according to a policy, priority, or round robin, and then asserts a grant line to the chosen master. The controller adds a small fixed latency, typically 1 to 2 clock cycles, but greatly simplifies device design because they do not need complex arbitration logic. Bus contention resolution and deadlock prevention techniques. Back-off algorithms. When two devices discover they collided, both try to drive the bus, they wait a random amount of time before returning. Similar to cars backing up at a four-way stop, Ethernet's exponential back-off is a classic example. Priority encoding. Assign fixed priorities. Higher priority devices can preempt lower priority ones, preventing deadlock, where each device waits forever for the other. Timeout counters. Each master starts a timer when it requests the bus. If the timer expires without grant, the master aborts and retries, ensuring no device is stuck forever. Deadlock-free resource allocation graphs model the bus as a resource use algorithms, such as Banker's algorithm to detect cycles before granting a request. Arbitration with fairness guarantees rotating priority, ensures every device eventually gets a turn, eliminating starvation, which can lead to deadlock-like situations in multi-master systems. Data transfer modes. Synchronous transfer. Both sender and receiver use a common clock. Think of a marching band stepping in time. Each step clock edge moves one data word. Pros: predictable timing, high bandwidth. Cons: both ends must share the same frequency. Asynchronous transfer, no shared clock. Devices use hand-shaking signals, request acknowledge, to indicate when data is ready. Like two people passing a note, one says ready and the other says got it. Lower speed due to extra control cycles, but more flexible for devices with different speeds. Pipeline transfer overlaps phases of multiple data words. Imagine an assembly line where while one worker paints a car, the next worker starts welding another. The bus can accept a new address or data each clock while previous data is still propagating, increasing throughput roughly to width times frequency after the pipeline fills. Burst transfer, a series of consecutive data words sent without rate, issuing the address for each word. Similar to buying a pack of groceries in one trip rather than many trips. Used in SRAM, PCI Express, etc., to exploit locality and reduce address overhead. Bus width, frequency, and throughput calculations. Definitions. Bus width W, number of parallel bits transmitted per bus cycle. For example, 32-bit, 64-bit. Frequency F clock rate of the bus in Hertz, cycles per second. Throughput T maximum raw data rate, measured in bits per second, BPS, or bytes per second, BPS. Basic formula: T equals W times F. If W equals 64 bits and F equals 100 megahertz, then T equals 64 times 100 million equals 6.4 gigabits per second, approximately 800 megabytes per second. Effective throughput. Real systems incur overhead, address phases, wait states, protocol bits. Effective throughput equals T raw times useful data cycles divided by total cycles. Example: a 32-bit bus runs at 150 megahertz, but uses 2 cycles for address and 1 for data in a 3-cycle transaction. Effective throughput equals 32 times 150 megahertz times 1/3 equals 1.6 gigabits per second. Address phase: the master places the target address on the address lines and asserts ADDR STB, address strobe. All slaves listen. The one whose address range matches will respond. Control phase: signals such as red/write, byte enable, and lock are asserted. This tells the slave what kind of operation is requested. Data phase: for a read, the slave drives the data bus. For a write, the master drives it. Handshake signals data ready, ACK indicate when the transfer is complete. A typical timing diagram simplified. The address appears on the first rising edge, control on the second, and data on the third. By counting clock cycles between address and ACK, you can compute the latency of a transaction. Interpretation tips. The width of the shaded region between address and ACK equals the number of cycles the bus is occupied. If a wait state signal wait is asserted, the data phase is stretched, increasing latency. In pipelined modes, a new address can appear before the previous ACK is received, overlapping phases. Multi-master bus systems and priority schemes. Fixed priority. Each master gets a constant rank, for example CPU greater than DMA greater than IO. The arbiter always grants to the highest rank requester that is active. Simple but lower rank devices may starve under heavy load. Dynamic priority. Priorities change based on runtime conditions, for example number of pending requests, QoS requirements. The system may boost a peripheral's priority when latency-sensitive data is pending. Rotating round-robin priority. The grant order rotates after each successful transaction, giving every master a fair slice of time. Similar to taking turns at a round table. Guarantees bounded waiting time and prevents starvation. Implementation example. In the AMBA AHB Advanced High Performance Bus, a HBUSREQ signal from each master is fed to a priority encoder. The encoder can be programmed for fixed or rotating schemes via HBURST register. The bus arbiter then asserts HGRANT to the selected master. Bus error detection and correction. Parity bit adds a single extra bit to each data word. Even parity makes the total number of 1 bits even, odd parity makes it odd. The receiver recomputes parity and flags a mismatch. Simple detects any single bit error but cannot correct. Cyclic redundancy check, or CRC, treats the data word as a polynomial and divides it by a predefined generator polynomial. The remainder is the CRC bits. The receiver performs the same division. If remainders differ, an error is detected. CRC can detect multi-bit burst errors. For example, CRC32 catches all 1-bit, 2-bit, and most 3-bit errors up to a 32-bit burst. Checksums add all data bytes together modulo some base and send the sum. The receiver adds again and compares. Easy to implement, but weaker detection capability compared to CRC. Error correction codes, or ECC, are more advanced schemes like Hamming code or Reed-Solomon. Add enough redundant bits to not only detect but also correct a limited number of bit errors. For example, single error correct, double error detect, SECDED, used in DDR memory. Practical use. Modern CPU caches and DRAM employ ECC to correct single-bit flips caused by radiation. PCI Express uses CRC32 for each packet and can request retransmission if a CRC error is flagged. Total bits per burst equals 128 bytes equals 1024 bits. Bus raw throughput equals 64 bits times 200 megahertz equals 12.8 gigabits per second equals 1.6 gigabytes per second. Time to transfer 1024 bits equals 1024 bits divided by 12.8 gigabits per second equals 8 times 10 to the minus 8 seconds, which is 80 nanoseconds. Each data phase transfers 8 bytes equals 64 bits, which takes 1 cycle. Number of data phases equals 128 bytes divided by 8 bytes equals 16 cycles. Total cycles equals 2 address cycles plus 16 data cycles plus 1 wait cycle equals 19 cycles. Bus cycle time equals 1 divided by 200 MHz equals 5 nanoseconds. Total time occupied equals 19 times 5 nanoseconds equals 95 nanoseconds. Utilization equals 80 nanoseconds divided by 95 nanoseconds times 100%, approximately 84.2%. In a parallel arbiter with 8 request lines, the priority encoder resolves the request in 2 clock cycles. If the clock is 150 MHz, what is the worst-case latency from request assertion to grant? Solution: 2 cycles times 1 divided by 150 MHz equals 2 times 6.667 nanoseconds equals 13.33 nanoseconds. A 32-bit pipeline bus can issue a new address each cycle after an initial pipeline fill of 3 cycles. At 250 MHz, what is the sustained data rate for a long burst? Solution: sustained throughput equals 32 bits times 250 MHz equals 8 gigabits per second, approximately 1 gigabyte per second. The initial 3-cycle latency is negligible for large transfers. Why is a token passing protocol inherently deadlock-free? Because only one device holds the token at any time, guaranteeing exclusive access to the bus. No 2 devices can simultaneously request the bus, so there is no circular wait condition, the classic necessary condition for deadlock. Explain the difference between a synchronous and an asynchronous bus in terms of timing diagrams. In a synchronous bus, the timing diagram shows a regular fixed-interval clock edge. Address, control, and data signals change only on specified clock edges, for example, rising edge. In an asynchronous bus, the diagram shows handshake signals such as request and acknowledgement. The interval between a request and acknowledgement can vary, and there is no global clock governing when data is valid. If a 16-bit bus runs at 50 MHz and employs a 4-to-1 time multiplexed address bus, what is the effective address bandwidth? The address bus carries 16 bits every 4 cycles, so address bandwidth equals 16 bits divided by 4 times 50 MHz, which equals 4 bits times 50 MHz, which is 200 megabits per second. What is the purpose of a wait state signal, and how does it affect bus throughput? A wait state inserts extra idle cycles when a slave is not ready to accept or provide data, for example, slow memory. Each wait state reduces the number of useful data cycles per unit time, decreasing throughput by a factor of useful cycles divided by the sum of useful cycles and wait cycles. Describe how a rotating priority scheme prevents starvation in a multi-master system. After a master completes a transfer, the arbiter moves the highest priority to the next master in the rotation. Over a full round-robin cycle, every master receives a grant, ensuring that no master can be continually bypassed by higher priority devices. Model answer format. For each exam question, start with a concise definition, provide a short analogy if helpful, then give the precise technical answer. Use bullet points for clarity when listing multiple items.